Hi, this is Martin from MB Drive Services. In this video I would like to talk about variable frequency drive system or variable speed drive system, and particularly the main system components. For that purpose I have prepared this diagram as an example of a drive system, and I will explain it with the help of this chart. So we will start from the left and go to the right in the direction of the power flow. So on the very left we have the electric grid. This is where the electricity comes from. Then there is a circuit breaker that allows the connection and disconnection to and from the grid. And it provides also the protection functionality. The first system component I will talk about is the input transformer number 1, as depicted here, a multi-winding transformer typically, so with more than just one secondary winding. In this case I'm showing here 4 secondary windings, with the phase displacement in between them to help to eliminate certain harmonics. The main function of the transformer is to adapt the voltage, so the grid voltage to the secondary voltage that matches the nominal voltage at the input of the rectifier, what is expected. The transformer, however, has multiple functions, not just the voltage adaptation. It has this phase shifting function to eliminate certain harmonics from the spectrum. The short circuit impedance is also limiting the fault current from the grid, so it can be also part of the protection concept. The impedance is also smoothing the harmonics. There can be also electrostatic shield between the primary and secondary winding, and so on. So the transformer has multiple functions that are all important for the drive system. Number 2 is the VFD itself. So this is the magic component where the frequency conversion happens. The input electric power to the VFD has a fixed frequency, typically 50 or 60 Hz, depending on the country where we are. And at the output it supplies electric power to the motor with a variable frequency. And in that way we can control the speed and torque of the motor. That brings me to the component number 3, which is the electric motor. This is the component that converts the electric power into the mechanical power in terms of torque and speed that is then driving the load. Each of the system components has certain losses that are dissipated, and although they have generally very high efficiency, we can talk about nominal efficiency in the range 97 to 99%. It's still a certain amount of lost power losses that need to be evacuated from the source in order to maintain a stable temperature and guarantee the proper functionality and lifetime. So this is shown here as number 4. Here I'm just showing example of simple sketch of a heat exchanger. Generally this is the cooling system of each system component, and this is also can be seen as a recooling system of the electric room, for example, to maintain also stable temperature and stable ambient conditions in that electric room. Number 5 is input harmonic filter. Is shown with a dashed line. That's because most of the modern medium voltage VFDs do not require a harmonic filter, because they already minimize the harmonics on their own level. So by the topology of the VFD, like using a multi-pulse rectifier in combination with the multi-winding phase shifting transformer, or using active front-end VFD with suitable modulation to eliminate those harmonics. Nevertheless, there are some cases where the harmonic filter might be required. That's why it's shown here. The filter has always dual functionality. One function is to absorb the harmonics, or to provide a path for the harmonics, so they flow into the filter branches. It can be one or more branches, rather than going into the grid. And this is what we want, because if they flow into the grid, then they are causing distortion in the grid. So we want to trap them in the filter. And each filter inherently also provides some reactive power capability, so this can be used for reactive power compensation and power factor correction. If you would like to learn more about those key system components of a drive system, we have a dedicated webinar series for that. It's called KYDS, standing for Know Your Drive System. It consists of 5 parts, exactly as we have those 5 numbers. Each part is a lesson that takes 1 to 1.5 hours, and you will learn in detail about each system component individually, about some classification, about the design, some features, performance, and so on. We have launched the webinar series in 2022. It's actually our most popular webinar up to date, and we have recently revised it based on the experience we had from providing the webinars live and having the feedback from the participants. So we have now kind of KYDS 2.0, which is even better than the previous version. You can also watch it on demand, so in a time slot that is suitable for you. You will find description about the KYDS webinar series below the video in the description. If you are interested, just go in and learn more about it. Thank you for watching.